Hello and welcome to my long-term presentation. I'm Keith Pawlowski. My long-term tests sound deadening with stuff I add around the house. So a little background information, especially in a place like a recording studio, background noise can be a big problem. But professional sound absorbing panels can be very expensive, so I wanted to know the best way to make my own. So the way I'm going to do this is I'm going to use a cardboard box to simulate a room. So I'm going to try and lower the sound level of the noise from inside the box as much as possible. So to do this, I'm going to try increasing the surface area volume ratio of the box. What this is going to look like is where green is your surface area and red is your volume down here. As I add structures to the side of the box, the green surface area gets larger and the red volume gets smaller, and that ratio number is going to go up. So to do this, I'm going to need a cardboard box, speaker, sound generator, microphone, lots of cardboard strips, and a whole lot of tape. So the way this is going to look is I'm going to put the speaker inside the box, hook it up to the sound generator, hang the microphone above the box, and then what I'm going to do is I'm going to take the sound generator and set it to make a sound from frequencies 300 hertz to 1500 hertz in intervals of 300, which the 300 to 1500 is about the range of the human voice. So I'm going to measure the sound level from what the microphone picks up, and then between trials I'm going to add more ridges to change that surface area to volume ratio. So taking inspiration from the sound absorbing panels, this is what I'm going to call a ridge. It's a couple cardboard strips that I taped together in a triangle shape. So these are the dimensions for what those are going to be. Now, here's the math of what I'm doing here. So finding the surface area was a little bit tricky because you have to not only add the dimensions of the cardboard, but also subtract from where the cardboard covers the box. So, and on top of that, my math can't be quite right because the way I measured the cardboard of just straight measuring across, bending it over, there's some issues with the measuring. And that, of course, comes to play when calculating the volume, too. But all this math on the side here is just me trying to figure out what those numbers are, coming up with a way to find the ratio for each of the ridges. So here's my data. I'm grouping it here by frequency. So here lower on the y-axis means quieter, which is what I'm looking for. But other than kind of like general trend lines, you can't tell which ridge configuration is quiet, makes the sound quieter by the way it's organized. So I went and averaged all the points, but you still can't really tell what's going on. It's a little cleaner, but here I have it sorted by the ridges instead of the frequency. So once again, you get a bunch of different shapes, but which one's quieter, you can't really tell. So I had to come up with something I'm going to call net sound absorption. So what this is a calculation I did, and I took the sound level for a number of ridges and subtracted from it the sound level for the empty box. So I repeated this for every frequency and then added up all the differences, and what I got was a number that showed me generally how good each cardboard configuration did. So on this graph, lower means quieter, and negative sound actually means that it was absorbed. So as you can see for the cardboard, this didn't happen at all. The cardboard every single time amplified the sound, which is the opposite of what I was looking for. So I need to go back to the drawing board here. So first I wanted to figure out why there was so much variation in my data on the same points. So when I was testing the same frequency with the same number of ridges, sometimes the sound level would be very, very different. So it turns out that this was caused by me turning the dial. So when I moved the rather small dial and missed the point by even the smallest amount, it could drastically increase or decrease the sound level. So despite this, though, I could clearly see that cardboard was not going to work. So I needed to change up what I was doing and get some new materials and a new claim. So I decided to go with old towels. So to quantify these towels, I'm going to treat them as two-dimensional, measure length, and width only. So what I think this is going to do, the more towels I add to the box, the sound level is going to decrease proportionally. Now, before I did this, I retested the empty box, just to be sure nothing got off when I was over the course of however many days I was testing this. So what I found was that the empty box was very different from when I tested it before doing the cardboard. I really didn't have any explanation for this, but my faith in my data was shaken greatly. So starting off, I wanted to use rags simply because I had 4 identical ones. It would keep the differences in between trials to a minimum. So for the first setup, you can't really see a whole lot with the data again, but it does look pretty similar to the empty box. So here's setup 2. 2 rags are used. Once the shape changed quite a bit, but we don't really know until we get that net sound absorption number. 3 and 4, same thing, different graphs. Looks like I kind of messed up on the bottom 600 hertz trial, but now here's where things get a little weird, because the singular towel actually did some significant sound absorption according to my data, when the rest, more towels, amplify it at different rates. So I couldn't imagine what's going on, how the more is amplifying it, but only less as more go along. But all I knew was that this is not consistent. This isn't going to work for actually deadening sound. So I decided to use old bath towels instead because they're heavier. The old rags are actually kind of threadbare, so getting a heavier towel I think would do more. I just wanted to see what would actually work here. So with these 4 trials, I basically threw caution to the wind. I chose to ignore the towel placement as a possible variable. I just assumed that every towel is going to absorb the same, no matter if it's folded up like on the right 2 or laid out on the left 2. So it's also worth noting that on the left 2, I placed the speaker on a little piece of cardboard. This was because that changing the surface that the cardboard was placed on varied the volume of the speaker significantly. So as for these results, mission success. There was some serious sound absorbing going on. Heck, you could even say that looks kind of linear, suggesting that my claim might actually be true, but the lack of data points kind of makes it tough to say whether or not to prove it definitively. So I added a couple more points from the first trial onto the end here. It doesn't really change a whole ton. You can kind of see a line. So in the end, testing cardboard didn't work at all. In fact, it worked so poorly, you might even be able to say it was a bad idea. But the towels at least look pretty good. But at the end of the day, I just don't trust my data. Like, I ended up testing the empty box 3 different times on 3 different occasions and over the course of the entire experiment, and all of them were different. So at least looking at the first to last one, at least I can say I got better at turning the dial more precisely. But overall, though, I think my data makes it hard to draw conclusions to support or deny any of my claims. Thank you.